Welcome to Math 2318. This is section 6.1. In this section, we're looking at the dot product with the dot that you see there. So the dot product between two vectors, you essentially multiply component by component. 5 times 5, 25, minus 1 times minus 1, 1. Minus 5 times minus 5 is a positive 25, and the sum is 51. The dot product of x times w. Now, one interesting thing is the dot product is commutative, so even if you did w times x, you would end up with the same number. Alright, so 6 times 5, I got minus 2 times minus 1, and 1 times a minus 5 to give me a number of 27. And then they asked us to calculate this ratio of the two dot products. So that's 27 over 51, but you can take a 3 out of the top and the bottom. And this cancels and we get 9 over 17. Now we can also find the magnitude of a vector. And so this magnitude is the square root of the dot product. Okay, so the magnitude of W is simply w dot w and then the square root. And so 2 squared minus 6 squared. And so I've got 8 plus 36, so square root of 44. And so I can factor a 4 out of that, and the square root of 4 is 2. So again, to find the magnitude or the length of the vector. So supposing I have a vector v and it points off somewhere. So here's vector v. What if I wanted to find a vector that points exactly in the same direction? So I want a vector pointing exactly in the same direction as vector v, but I wanted to have the property that the magnitude of that vector is exactly 1. And that's the key word here. We want to find a unit vector pointing in the same direction. Well, to find that, we simply take the original vector and divide it by its own magnitude. So the magnitude of vector v, call this vector v, I square each of the components, all right? So that's the square root of 28,900, which you can calculate to be 170. And so I essentially have 1 over 170 times each of the components. So the zeros would cancel. I get minus 8 over 17 and 15 over 17. Again, we're looking for a vector that points in the same direction as the one we were given, and its magnitude is exactly 1. Alright, we repeat the process here in question 4. So here's vector v. I need to find the magnitude. It's a bit of a pain because of the fractions. I need to square the first term, square the 3. 36 squared is 1296 over 25. Getting a common denominator, multiplying 9 by 25, top and bottom. And so I get the square root of 1521 over 25. Turns out the square root of 1521 is 39, and the square root of 25 is 5. So I've got 1 over that number, which means it's going to flip. And so now I have 5 over 39 multiplied by each of the pieces. For the top one, the 5's cancel. I get 36 over 39. And the second part, I've got 5 times 3 is 15 over 39. So take a 3 out of the top and the bottom, and that reduces in that way. So again, this is a vector pointing in the same direction as v, and it has the additional property that its length is exactly 1. In question 5, we would like to know if given two vectors, are they orthogonal? Orthogonal is another way of saying that the two vectors are perpendicular or not. Well, one way to find out if they are perpendicular is to check the dot product. If the dot product calculates to be 0, then in that case, the angle between the two vectors is 90 degrees, and they would be orthogonal. Alright, so A dot B is, in this case, so 4 times minus 5, 2 minus 2 times minus 5, and I get a minus 10. So A is not orthogonal to B. They are not perpendicular. Alright, what about question 6 here? Same deal, let's take the dot product of these two vectors and see. 10 times 1 is 10. I got a minus 9, minus 1. So yes, the dot product is 0. So the two vectors are orthogonal, or another way, they are perpendicular. Alright, question 7. Question 7 gets a bit larger here. Same deal, we're looking for the dot product, and so you can grind through multiplying term by term. The dot product turns out to be 104, and so no, they are not perpendicular or orthogonal. Now you'll also see, so right now we talked about vector v times dot product with u. We've seen how to do that component by component. It's u1 v1 plus u2 v2 as far as we want to go, un vn. Another way of doing this is the dot product can be thought of as the magnitude of u times the magnitude of v times the cosine of the angle that's between them. So that's another useful tidbit. If here is vector u and here's vector v. So it can be done component by component, or you could think of it this way.